name is Diego Gallego. I'm going to speak about this paper by Giudice and Ratazzi, and also I'm extracting some information from this nice review by Liuti. And if you want to go through and understanding well the systematics of the computation, I invite you to read these very nice introductory notes by Matteo Bartolini, and also this paper by Schiffman and Hisaro. So the idea is going to be the playground of supersymmetric field theories. So let me start with some motivations and invitation to supersymmetry. And so imagine that you are studying the nature, and in nature we have found that the more detailed is the observation to nature, the more symmetric is. We have several examples, like electromagnetism, that is actually a combination of electric and magnetic fields. But here, as a more focused example, is the fact that when we go to higher energies, the electromagnetic symmetry becomes the electroweak symmetry, and we expect at higher energies to have a further higher symmetry like randomification. So a very common question here would be, what is the largest symmetry that the nature can have? And this question has made in the late 60s and mid 70s, and the answer is that if you want to enlarge the most symmetric way the nature, the symmetry should be something that mixes bosons and fermions. So if you want to have a non-trivial quantum field theory that has a mass gap, then the largest thing that you can have is something that mixes these states. And this is what we call supersymmetry. Okay, supersymmetry has many appealing features. First of all, it's very nice, it's very appealing as a way of construction. It's a very restricted theory, it has aesthetics, has candidates for dark matter, has a very natural emerging of gravity that we call supergravity. In fact, when we go to a local version of supersymmetry, we get supergravity. Also, a very well-known feature of supersymmetric theories is that under quantum corrections are very stable, are far more stable than the usual field theories, and they make, in particular, for example, they come with the solution for the hierarchy problem of the standard model, but also they allow to make computation more easy. Okay, another appealing feature is the fact that it's an essential feature for the consistency of string theory, that is the theory that has more advantages to treat quantum gravity. However, there's a point. If supersymmetry is indeed a exact theory of nature, we have the same number of bosonic and fermionic degrees of freedom. And moreover, these degrees of freedom that are connected by the symmetry should have the same quantum numbers and the same masses. And that's the point, because if this is the case, we should see the superpartners of the standard model particles. For example, the electron should have a scalar particle that has the same charge and the same mass, but we haven't seen them. Therefore, we conclude that supersymmetry, if it is indeed a symmetry of nature, should be a symmetry that is at some point spontaneously broken, that leads to a splitting of the masses, and you have the standard model particles and its superpartners that are very heavy, and we haven't observed them in experiments so far. So if you want to connect these theories with experiments, you have to compute these masses of the superpartners, and these are something that we call soft masses or SUSY breaking effects. And this usually is very hard to compute, but here the discussion of this article is to a technique to compute these soft masses, these supersymmetric breaking terms, in a nice way, using supersymmetry, that is a very restricted theory that allows easier computations. So let me now really start with the outline of the talk. First of all, I want to give some formalities of the supersymmetric construction. Then I will introduce, do an invitation to the way that we proceed to compute the soft terms. You go into the superspace. Then I will introduce what we call the messenger's paradigm in the context of gauge mediation, and we will see how, if you want to compute in the usual way the soft terms, you have to do very hard work. But then, if you use the supersymmetry techniques, we will see that usually is easier. So, as I said before, supersymmetry is a symmetry that mixes bosonic and fermionic degrees of freedom, and this formally is done by enlarging the Poincare algebra by introducing two fermionic operators, and you have extra terms in your algebra. But these fermionic operators then, for example, commute with the momenta, and leads to some transformation of the fields, where you have here a fermionic parameter in order that the statistics in both sides are of the same kind. So with this guy in here, you see you have an enlarged algebra, but this enlarged algebra, when applied to the fields, you see that the algebra doesn't close on shell. Okay, only off shell. Sorry. It only closes on shell. In order to get an algebra that closes off shell, you have to introduce the so-called auxiliary fields. So are some non-dynamical fields that enlarge the supermultiplets, the multiplets of supersymmetry, and allows a closing of the algebra off shell. So you introduce these auxiliary fields that are not dynamical, and these auxiliary fields enlarge the supermultiplets, and these are the off-shell SUSY multiplets that they contain the same numbers of degrees of freedom, fermionic, and scalar degrees of freedom with the same contour numbers, because these operators commute with the internal generators. Okay, as I said, since these guys commute with the momenta, then the masses of all the components of the multiplets should have the same mass. But I want you to notice here that these auxiliary fields also will tell you when supersymmetry is spontaneously broken. Indeed, when you check the transformation of the fermionic part of the multiplets, they transform in this way. Okay, so if this guy acquires a non-vanishing expectation value, you get something that transforms non-linearly under supersymmetry. That is a special feature of spontaneously broken symmetries. Okay, however, there's a very nice way to work supersymmetric theories, and this is going to the superspace, something that in particular Salam and Strade built. And the idea is that you extend the space-time adding some extra dimensions, but these extra dimensions are not usual ones, since they are Grassmann variables. It means that they're anti-commute. Since they anti-commute, you cannot have powers larger than 2 in these variables. So now instead of having fields that depend on the space-time, you have something that we call superfields. And these superfields actually depend on the space-time and the extra coordinates. And we can expand this. As I said, you can have larger than 2 powers. And here I'm just speaking about 2 special kinds of superfields, something that we call chiral and something that we call real. Okay? So this guy depends only on thetas, this guy depends on thetas and theta 1. So with this, in this superspace, actually it's very simple to express everything. In particular, notice that here you have the elements of the supermultiplet, okay? And here this guy and this guy are going to be the auxiliary fields for the real and the kernel part. And they are going to tell you when this is going to break or not supersymmetry. So in superspace, you can write any Lagrangian of any supersymmetric theory up to 2 derivatives using only 3 elements. The first one is the superpotential that depends in the kernel fields and is an holomorphic gauge invariant function. The second one is the Keller potential, that is a real function that depends not only depends in the kernel fields but also can depend in the real fields. And the gauge kinetic function that depends is an holomorphic function as well. So any theory, supersymmetric theory, up to 2 derivatives can be written in this way. Okay? So here you have the Keller potential, here the superpotential, here the holomorphic gauge function, kinetic gauge function, where this guy here is going to play the role of the field strength. You can extract this guy from the real vector field, where you have the spinor, the auxiliary field, and here the field strength for this guy, for the vector field. So you have here some integrals in the theta, in the extra Grassmann variables, and these integrals actually obey some rules. But something that I want you to see in here is that integrating over theta is the same like taking derivatives. So if you have a theta squared integral, is like taking only the theta part, the auxiliary part of this chiral superfield. So with this background, let me now go to the real point of this talk. Imagine that you have a model, a supersymmetric model, and here we have the simplest one, that is the Wess-Zumino model, where you have the Keller potential in here and some superpotential. And here, in principle, this guy here and these two here are in principle just numbers. But I want now to extend these numbers and think on them like if they were fields. Actually, superfields. So this set function, this is going to be the wave function of these guys. Actually, is going to be some number plus some part that depends on the theta on the theta, in the theta direction, that are going to play like the role like a superfield, like an auxiliary part in here. Okay. The same for the mass in here. That is going to have a mass term and an auxiliary part, and the coupling as well. So what's the idea with this? For example, with this we can ask if the theory is corrected at quantum level. But now that these are not just couplings but are fields, we can realize something that before we couldn't. Actually, now that they are fields, notice that we see that there are some symmetries. Okay, imagine these charges under this scaling symmetry and these charges on this R symmetry, and you see that this theory is invariant under this transformation. Since this theory is invariant under this transformation, we may ask if the superpotential can be corrected at quantum level. Any correction to the superpotential would come in this way, satisfying these symmetries in here, and we can make the expansion in powers of the fields, so you have something like this, just in order to satisfy these symmetries. However, as you see, if these terms and these ellipses here, when you take lambda to 0 or when you take m to 0, are divergent, so they cannot appear there. And what you remain with is the original superpotential. It means that the superpotential is not corrected by quantum corrections. Therefore, the only corrections in the quantum theory will come from this guy. Okay, if you correct the theory by quantum corrections, the only guy that is going to transform is this one. Just so you see, some very nice feature of these supersymmetric theories is that it's very restricted, and something that you expect to vary in many ways actually is very rigid. In this case, only the wave function will vary. Now imagine that we want to extract what is the way that this wave function is changing. Actually, by the symmetries and just by scaling the analysis, we know that the only way that the bare wave function can depend on the scale is with this form. Okay, here I have the coupling, the wave function, and here I have the ultraviolet cutoff scale, and here I have a matching scale in the system. So since these guys cannot depend on the scale, is the bare wave function, you get a RG equation for this Z that has this claim, where here I just call this gamma, recalling the anomalous dimension as we called before in the course. Now there's a very subtle difference. This guy in here is not a number, now it's a superfield, because this guy is a superfield as well. However, imagine that this guy actually breaks supersymmetry. If it breaks supersymmetry, it means that the auxiliary part from it is non-zero. And the auxiliary part for a real superfield, as is the wave function, comes with this, accompanied by this theta squared, theta bar squared, and we call it M because it's going to introduce a mass term for the Wess-Zumino field. So if this is the case, notice that the theta squared part of this guy, of this equation, will come as an equation for M. So if you take the theta squared, theta bar squared part of here, and the same in here, you will get a RG equation for M. Okay? So this supersymmetry breaking mass for the Wess-Zumino field is going to satisfy this RG equation that has this form. Okay? Now the only thing that remains is to know this anomalous dimension, that you can compute it by the standard techniques that we learn. And now now are functions, they are not superfields, and we computed, for example, that one loop for this theory, and we get this. So now we can extract this expression, and we get the RG function, the RG equation for the mass, soft mass in here. So here you see, I'm just supposing that the theory satisfies supersymmetry and extract information about the soft supersymmetry breaking term for the Wess-Zumino term. Now the thing comes is, I want to suppose that this M is introduced by some extra field that breaks supersymmetry at first instance, and then we will see how this comes out. And this is the paper by Judy Chen and Ratazzi. Okay. However, notice that in general, not only Z, the anomalous dimension will have the wave function will have a supersymmetric breaking term. Actually, also the mass term and the coupling can have as these supersymmetry breaking terms, and we'll have a potential that's this form. And here I have again the mass that I was advertising before for the Wess-Zumino field. We have something that we call E terms in here, and this has some expressions in terms of the wave function, in terms of the mass term and the couplings, but these are actually the physical couplings. And again, you see, they are going to depend on the anomalous dimensions here. Okay, so as before, just you compute the anomalous dimension by standard techniques, and you get the running of the soft terms. Now let me speak about just the feature of the gauge mediation. So imagine that supersymmetry is broken at some hidden sector. A standard model doesn't break supersymmetry, but there's some fields that communicate coupled with this SUSY breaking sector and coupled as well with the standard model, but they couple only through gauge interaction. So the supersymmetry breaking effects here are communicated to the standard model through these messengers. So if you want to compute the soft masses and the soft breaking terms, you have to compute something that are actually loops. Okay? So for example, the superpanel of the gauge vectors or the Lagrangian, you can compute the mass that they acquire using calculating this loop in here, where these are going to be the scalar and the fermionic parts of this guy fields are here, and the same here, some two loops computation. So in general, these are going to be rather hard computation that people can do, but if you go to higher loops, they can be really involved. So the idea is here, imagine that actually we have this spurion field that lives in the hidden sector, and this spurion field couples with the messengers. This coupling actually, if we suppose that this guy breaks supersymmetry, has a non-vanishing auxiliary part, but also have a non-vanishing part here, and this actually gives a non-zero mass for the messengers. And now we are going to suppose that this mass in here, that the messengers get, actually is very large compared to the supersymmetry breaking scale. So if you now you take this theory and integrate out the messengers, what you have is a theory that is supersymmetric because of this hierarchy. Since the theory is supersymmetric, you have that satisfy the rules that I said before. In particular, the coupling with the gauge vector comes in this way, okay? And now this guy, now I can compute the masses for the Lagrangians in here, just taking the theta squared part on here. And this is just this result, okay? In here I have taken into account the canonical normalization for the gauge fields. Now, okay, I just use the fact that this guy should be a holomorphic, only can depend in the x, not in the x bar of this guy. So this is a chiral field, only can depend in the x and not in the anti-holomorphic part of this x. Now, this gauge kinetic function is representing also the gauge coupling, and in particular the real part of this guy, when we compute it in numbers, not in superfield space, it gives the coupling of the gauge function, of the gauge interactions, and we know how this guy runs. Actually, we compute the one loop running of this coupling. Okay, here I have some ultraviolet cutoff, and I have a matching part, and you see in here is the part where we integrate out the messengers. So in here is going to be the running of the fields before the messengers are integrated out, and in here is the running between the messenger scale and the matching scale. So these are two beta functions, above where we have messengers, below where you don't have messengers. However, now this is at the function level, but we want to uplift this in the sense that we promote this to the superspace, and we do an analytic continuation. So where with the m appears, now we are going to replace it, this m, now we are going to replace it by x, and we have the full x dependence of the gauge kinetic function that I have here. Okay? So now I have the gauge kinetic function, the full dependency on x, and I can compute this, derivatives here that give me at one loop level, because this is a loop, one loop computation, at one loop level, the Gaussian part. And this is actually concise with the computation that you will extract by doing the loops and the explicit computation, but you see here is just a matter of computing this RG evolution of the couplings. Okay, so we were able to compute the Gaussian masses. Okay, now we would like to compute the soft-scalar masses, and for doing this we have to compute this guy here. Okay, remember this is a superfield. Now it's a real field, so can depend in X, but also in X, the antilomorphic part, and we can expand this in powers of theta, and you get something like this. Okay, now taking the theta bar squared, theta squared, so we can take this part, and after canonical normalization you will get this, for these guys, a mass term of this way. And this is the expression for the mass term, soft-mass term. Again, I'm just using the fact that these guys should be real, should depend on these two guys, and also in the scaling here. Actually, when we did this, in the canonical normalization part, by canonical normalizing, these two terms disappear, but you introduce a variation in the superpotential that at the end reflects as an extra term in the potential. That is an E term. The E terms is another soft terms that in this case, when you compute this now in the superpotential part of the Lagrangian, you get an expression for the E terms like this way. Again, after the canonical normalization that leads to this energy. So you see, if you want to compute these guys that I'm just showing here, you have to get what is the dependency of the anomalous of the wave function in X and X dagger, and this is done again by solving the RG equations at the level that you want. For example, you want to you have this is the equation, the RG equation for the wave function at a level of one loop, and you solve it again. Okay, it depends again in the RG equation for the couplings of the gauge theory, and you get that again we have the expression for them at one loop, so we can solve this guy and we get the expression for the soft masses and the E terms. Okay, that would one are going to depend again in the beta functions of the theory are above and below, after and before integrating the messengers. So these expressions again coincide with the computation that you do by doing the loops that I showed before. Okay, just to finish, let me do 2 comments. In this analysis, I'm just supposing that I'm regularizing the theory in some way that supersymmetry is still valid. And this way is something that Wess-Zumino already in the 70s, sorry, came with, and this is a kind of extension of this regularization that we learned before. Now it's a supersymmetric regularization. So if you want to implement this, you have to regard a supersymmetric preserving regularization scheme. And this analysis is very straightforward when you are stopping at the one loop level. When you go to higher loops level, you have to be careful, because now this scaling symmetries that I was telling before in the initial part of the talk now are anomalous, and actually what are going to be related to the couplings are not the gauge coupling, the gauge kinetic function by some R function, because you need some extra counter terms to cancel the divergences. Anyway, this can be done, this can be implemented, and this was studied again by Ratazzi and Giudice together with Luti and Arcanian. So let me conclude. So we see that using the fact that the messengers get a very large mass compared to the supersymmetry breaking scale, we have a theory that an effective theory that is supersymmetric and therefore is very restricted. And we can, without doing any computation, we know more or less what is going to be the dependency of the couplings in the theory with the fields that actually break the supersymmetry, the spurion fields. Okay? And this is what I'm saying here, that the holomorphicity leads to very direct expression for the soft terms, and this is what we express in here. So we know what are going to be the expression, and what remains is to get actually the explicit dependency of these guys in the spurion fields. And what we do here is just use the relation of these guys with the couplings, the actual couplings of the theory, and use the RG equations. And these RG equations actually relate the scales, the mass scales, with the couplings, and now by analytic continuation, now these scales are going to be treated as superfields, and we do the analytic continuation in order that where the mass scale appear, now this X appear. Okay? And this is what we do at the loop level, and we get the actual expression that people already computed before of this paper for gauge mediation of supersymmetry breaking. Okay, thank you very much. I hope you enjoyed and you get something from this talk.